You've been told that black holes are cosmic vacuum cleaners, that nothing can escape them, that once you cross the event horizon, you're gone forever. Pulled inexorably toward the singularity at the center, not even light can escape. That's why they're black. This is what every popularization tells you, every documentary, every textbook, and it's wrong. Or rather, it's incomplete in a way that changes everything. Because black holes do let things escape. They evaporate, they radiate, they shrink, and eventually disappear completely. Stephen Hawking proved this in 1974, and this discovery created the biggest crisis in theoretical physics in the last 50 years. A crisis we're still trying to resolve. I'm Leonard Susskind, and I've spent decades fighting about black holes, fighting with Hawking himself, fighting about whether information is destroyed, fighting about what really happens at the horizon. And what I'm going to tell you is that the simple story, nothing escapes, is wrong. Black holes radiate. They evaporate. And understanding how this is possible requires rethinking everything we thought we knew about space-time and quantum mechanics. Let me start with a classical picture. Einstein's general relativity predicts black holes. If you compress enough mass into a small enough region, space-time curves so severely that it creates a point of no return, the event horizon. Inside the horizon, all paths lead to the singularity. You can't escape, because escaping would require moving faster than light, and nothing moves faster than light. From outside, a black hole looks simple. It has mass, charge, and angular momentum. That's it. The no-hair theorem says these three properties completely describe a black hole. Everything else, all the details about what fell in, are hidden behind the horizon. The black hole has no memory of what created it. A black hole made from collapsed stars looks identical to one made from compressed gas or from anything else with the same mass, charge, and spin. This is classical general relativity. And according to classical general relativity, black holes are eternal. They don't evaporate, they don't radiate. They just sit there, growing whenever something falls in, never shrinking. But in 1974, Stephen Hawking applied quantum field theory to black holes, and he discovered something shocking. Black holes are not black, they emit radiation. Thermal radiation with a specific temperature inversely proportional to the black hole's mass. This is Hawking radiation, and it means black holes evaporate, they lose mass, they shrink, and eventually they disappear. How is this possible? How can anything escape from inside a horizon where escape is supposed to be impossible? The answer is subtle. Hawking radiation doesn't come from inside the horizon. It comes from just outside it. Here's how it works. Quantum field theory says that empty space is not really empty. It's filled with virtual particle pairs constantly appearing and disappearing. An electron and positron pop into existence, exist for a tiny fraction of a second, then annihilate. This happens everywhere all the time. In flat space, far from any black hole, these virtual pairs appear and disappear with no net effect. But near a black hole horizon, something different happens. A virtual pair appears just outside the horizon. One particle falls into the black hole, the other escapes to infinity. To a distant observer, it looks like the black hole emitted a particle. The particle that escaped is real, not virtual. It carries energy away from the black hole, and since energy is equivalent to mass, the black hole loses mass, it shrinks. This process continues. Pair after pair, particle after particle radiating away, the black hole evaporates. Now here's the crucial point. The particle that escapes never crossed the horizon. It was created outside, and it stayed outside. Nothing escaped from inside the horizon. The horizon remains a one-way membrane, but the black hole still loses mass and eventually disappears. This is how black holes evaporate without violating the principle that nothing can escape from inside a horizon. The radiation comes from just outside, from the quantum vacuum fluctuations near the horizon. Hawking calculated the temperature of this radiation. For a solar mass black hole, about 3 solar masses, the temperature is about 60 nanokelvins, at 60 billionths of a degree above absolute zero. Incredibly cold, far colder than the cosmic microwave background, which is about 2.7 Kelvin. So stellar mass black holes are actually absorbing more radiation from the universe than they're emitting. They're growing, not shrinking. But smaller black holes are hotter. The temperature is inversely proportional to mass. A black hole with the mass of a mountain would have a temperature around room temperature. A black hole with the mass of a large asteroid would be thousands of degrees. And tiny black holes, if they exist, could be incredibly hot, hot enough to shine brightly, hot enough to explode. A black hole with the mass of a large ship would have a temperature of billions of degrees and would evaporate in a fraction of a second in a burst of gamma rays. Now here's where the crisis begins. Hawking's calculations showed that the radiation is perfectly thermal. Thermal radiation is random. It carries no information about what created it. A lump of hot coal radiates thermally. The radiation doesn't tell you what the coal is made of or how it was formed. It's just random photons with a blackbody spectrum. Hawking radiation is the same. Perfectly thermal, random, carrying no information. But this creates a problem, a huge problem. Suppose you throw a book into a black hole. The book contains information. The arrangement of atoms, the words on the pages, the knowledge encoded in the text. In quantum mechanics, information cannot be destroyed. This is a fundamental principle. The time evolution of quantum states is unitary, reversible in principle. If you know the final state precisely enough, you can reconstruct the initial state. Information is conserved, but if the black hole evaporates into thermal radiation that carries no information, where did the information in the book go? It seems to have been destroyed. This is the black hole information paradox. And it's been the central problem in quantum gravity for 50 years. Hawking himself initially argued that information is destroyed, that black holes are exceptions to the rules of quantum mechanics, that we need a new theory. Most physicists, myself included, found this unacceptable. Quantum mechanics is too successful, too fundamental to abandon. So we searched for another solution. And the solution, we now believe, is that Hawking was wrong. Information is not destroyed. The radiation is not perfectly thermal. It's nearly thermal, but contains subtle correlations that encode the information about what fell in. The information escapes in the Hawking radiation. Not quickly, not obviously, but it does escape. Encoded in the quantum state of the radiation in ways too subtle to detect practically, but present in principle. This resolution depends on quantum entanglement and something called black hole complementarity, an idea I developed with colleagues in the 1990s. Let me explain complementarity. The key insight is that different observers see different things. An observer falling into a black hole crosses the horizon smoothly. From their perspective, nothing special happens at the horizon. They continue falling toward the singularity. They see the interior of the black hole. But an observer who stays outside never sees anything cross the horizon. From the outside perspective, infalling matter slows down, redshifts, and appears to freeze at the horizon. The information spreads across the horizon surface, and when the black hole evaporates, that information is gradually released in the Hawking radiation. These two descriptions seem contradictory. The infalling observer sees matter cross the horizon and enter the interior. The outside observer sees matter stick to the horizon and radiate away. Both can't be true, right? Black hole complementarity says both are true. They're complementary descriptions that apply to different observers, No single observer can verify both descriptions simultaneously. An observer who falls in can't compare notes with an observer who stayed outside because they can't communicate after crossing the horizon. This is similar to complementarity in quantum mechanics. Wave-particle duality. Light behaves as a wave in some experiments and as a particle in others. Which behavior you see depends on what measurement you make. But you can't see both simultaneously. The black hole version is more extreme. The complementarity is not just about the measurement choices, it's about which side of the horizon you're on. And it resolves the information paradox. From the outside perspective, information never enters the black hole interior. It spreads on the horizon and is encoded in the Hawking radiation. Information is conserved. From the inside perspective, you see an interior and you see things fall in. But once you're inside, you can't get information out to verify what the outside observer sees. Both descriptions are consistent with what each observer can actually measure. Neither is more fundamental. They're different slices through the quantum reality of the black hole. Now, this is where things get really strange. If the information is on the horizon and in the radiation, what about the interior? Does the interior even exist? In a sense, the interior is emergent. It's constructed from the quantum entanglement between early and late Hawking radiation. This comes from the ER equals EPR conjecture I mentioned before. The idea that entanglement creates wormholes. In the black hole context, the entanglement between Hawking radiation particles creates the geometry of the black hole interior. The interior is not fundamental. It's a holographic projection of information on the horizon. This is deeply connected to the holographic principle. The entire three-dimensional interior of the black hole is encoded on the two-dimensional horizon. An observer falling in experiences an interior because that's what the quantum state projects. But from outside, the interior doesn't exist as a separate entity. It's just a way of describing correlations in the radiation. Let me tell you about the firewall paradox because it made this even more confusing. In 2012, Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully proposed a problem. They argued that if information escapes in Hawking radiation, then old black holes that have evaporated more than half their mass, must have firewalls at their horizons. A firewall is a region of high energy density that would incinerate anything trying to cross the horizon. This contradicts the equivalence principle, the principle that says you shouldn't notice anything special when crossing a horizon. If there's a firewall, you definitely notice. You burn up. The argument goes like this. For information to escape, the Hawking radiation must be entangled with the information that fell into the black hole. But the Hawking radiation is also entangled with its partner particle inside the horizon because that's how Hawking radiation is created. Pairs of entangled particles, one inside, one outside. But quantum mechanics forbids a particle from being maximally entangled with two different systems. That's monogamy of entanglement. Something has to give. Either the equivalence principle is violated and there's a firewall, or information is destroyed, or something else happens that we don't understand. This paradox generated enormous debate, hundreds of papers, conferences, arguments, and we still don't have a universally accepted resolution. But progress has been made. Many physicists now think the firewall is avoided through quantum error correction. The information is encoded redundantly across the horizon and the radiation in a way that allows it to be recovered without violating monogamy. The details are technical, but the idea is that the quantum state of the black hole and its radiation is more complex than we initially thought. It has structure that prevents firewalls while preserving information. Another idea is that the interior of an old black hole is very different from what we naively expect. That the smooth interior described by classical general relativity breaks down in old black holes, that the interior becomes highly quantum, highly entangled with the radiation in ways that we don't yet fully understand. that crossing the horizon of an old black hole might indeed be different from crossing a young one. Not a firewall necessarily, but something strange. Now let me bring this back to the original question. Can anything escape a black hole? The classical answer is no. Nothing inside the horizon can get out. The quantum answer is more subtle. Nothing can cross the horizon from inside to outside, but the black hole can evaporate through Hawking radiation emitted just outside the horizon, and the information about what fell in is encoded in that radiation. So in a sense, everything that falls into a black hole eventually comes back out. Not in the same form, not in a way you'd recognize, but as quantum information scrambled and encoded in thermal radiation. If you fell into a black hole and it evaporated, billions of years later, your information would be in the radiation. Every atom, every bit of data that composed you, translated into correlations in photons and particles, unrecognizable but present. This raises a philosophical question. If you're encoded in radiation, are you dead or alive? You're certainly not alive in any meaningful sense. Your structure is destroyed, your consciousness is gone, but your information persists. Every detail about you is still in the universe, just scrambled beyond recovery. Let me tell you about black hole mining. This is speculation, but interesting. If Hawking radiation carries information, then in principle you could reconstruct what fell into a black hole by analyzing the radiation. You'd need to collect all the radiation, you'd need to perform exponentially complex quantum computations. But in principle, it's possible. You could mine information from a black hole by catching its radiation and decoding it. Of course, this is completely impractical. The radiation is nearly thermal. The information is encoded in subtle correlations that would require measuring the quantum state of every particle with impossible precision. And you'd need to wait for the black hole to evaporate, which takes trillions of times the current age of the universe for stellar mass black holes. But it's theoretically possible. Information is not lost. It's just hidden in the radiation. And here's something truly strange. The time it takes for information to come out is related to the scrambling time of the black hole. This is the time it takes for information to become maximally spread across the black hole's degrees of freedom. For a black hole, this time is logarithmic in the entropy. It's incredibly fast, the fastest scrambling possible in nature. Black holes are the ultimate information scramblers. Now, let me address the practical question. Will we ever detect Hawking radiation? For stellar mass black holes, no. The temperature is too low, the radiation is too faint. We have no hope of detecting it with any conceivable technology. The black hole would need to shrink to about the mass of a large asteroid before its Hawking radiation would be detectable. And it would take far longer than the age of the universe to shrink that much. But primordial black holes, tiny black holes created in the early universe, if they exist, could be evaporating now. A primordial black hole formed shortly after the Big Bang with an initial mass of about 1 billion tons would be evaporating right now. It would be hot, bright, radiating gamma rays. We've searched for such black holes. We haven't found any. This puts limits on how many primordial black holes exist, but the search continues. If we found one, it would be spectacular. A black hole exploding in a burst of Hawking radiation. Proof that Hawking was right, that black holes evaporate. Let me end with what black holes teach us about physics. They're laboratories for quantum gravity. They sit at the intersection of general relativity and quantum mechanics. Understanding them requires understanding how these two theories fit together. And what we've learned is that information is fundamental, that it's conserved even in the most extreme circumstances, that horizons are not what they seem, that the interior of a black hole might be emergent, not fundamental, that space-time itself might be woven from quantum entanglement. Black holes have forced us to rethink our most basic assumptions about space, time, and information. After 50 years of thinking about black holes, I'm convinced that they're telling us something profound about the nature of reality, that the universe is fundamentally quantum, that information is indestructible, that what looks like a three-dimensional interior is actually a two-dimensional hologram, that nothing truly escapes from inside a horizon, but everything eventually escapes through evaporation. Black holes are not the end of information. They're information processors, scramblers, encoders, and when they evaporate, they give back what they took. Not in the same form, but the information persists. Nothing is truly lost. Thank you for watching. Now you know why black holes both trap everything and let everything escape. Welcome to quantum gravity.